For the final time in higher maths. Grace, tell them what it's time for.
It's time for Maths with Mr. Thomas.
That's right! Here we are with chapter 15, lesson number 9. This is a review lesson for the logs and exponentials chapter. It is also the final lesson in this higher maths course. Woo! Which means we have made it to the end. High five. This review lesson, just like all the other review lessons, does not include every slide and every example, and I go over the examples very, very quickly, sometimes not at all. If there is anything you find you're unsure of, please look back at the individual lessons where I will explain everything in detail. But for now, let's begin. So before we moved on to logs and exponentials, I threw in this lesson. Surds and indices, a recap from National 5, something that you needed to be absolutely fine with before you moved on to this part of the higher course. These are your index rules from National 5, including flower power, and if there's anything you're unsure of, look back to that lesson, try those questions, make sure that you are okay before you move on. Exponentials is really where we start with logs and exponentials, and something that we already came across in chapter 3 was what an exponential is and what it looks like when you graph it. An exponential function is where you have f of x equals a to the power of x. The base is a, and a is not equal to 1 and is bigger than 0. X is your index. Hello! If you graph an exponential, you will see that if a is bigger than 1, then it is going to be increasing, and it looks something like this. If a is between 0 and 1, so 0 point something to the power of x, it will be decreasing, and it will look something like this. If it increases, it's a growth function. If it decreases, it's a decay function. Also, exponentials always pass through, if they are in the form of f of x equals a to the power of x, 0, 1 and 1a. You can see that both the increasing and the decreasing function, the growth and decay function, pass through 0, 1 and 1a. That's true for all exponentials in that form. The second thing we then looked at with exponentials was e. E is a special number in maths and two decimal places, like 3.14 for pi. It's a number that keeps on going, so to two decimal places it's 2.72. All the calculators have an E button, and we had to use that to answer various problems. Started off just using the E button, so if you had to work out e to the power of 4, dead easy, you just blinky blunky 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 blink, put it into your calculator, and you get your answer. What you'll find though is a lot of real life situations are modelled using a formula, such as this, with E in them. And you've got to be able to answer questions, worded problems which include E. A lot of the time you will use that E button on the calculator. So you're subbing values in and then you're answering a question. Again, if you want me to talk through this, look back to that lesson. That was it really for exponentials. It's the graphs of exponentials and it's E. After that, we looked at logarithms. Now a logarithm or a log function is the inverse of an exponential. So if f of x equals 2 to the power of x, its inverse will be log base 2 of x. 2 to the power of x equals 32, its inverse is log base 2 of 32 equals x. Something you have to be able to do is to be able to switch between them really quickly, and absolutely fine. Yeah! To do that, the correct mathematical way is to take whatever the base is. So here you can see you've got 32 on that side, and here you've got a base of 2 and an index of 5. Take whatever the base is, because it's base 2, you would take log base 2 of both sides. What that does is, because you've got log base 2 and exponential base 2, they cancel out. Log base 2 and exponential base 2 cancel, leaving you with 5. So you can rewrite 2 to the power of 5 equals 32 as 5 equals log base 2 of 32. So that's changing from exponential form to log form. A wee quick method that I quite like to use though, and I've used it for all the lessons, is base bottom top. And what you do is you can easily change from exponential to log form or log to exponential, and you always start with the base. So here we've got a base of 2. You then draw a line at the bottom across to the other side of your equation. So you'd have, if you wrote this in log form, it would be log base 2 of 32, and that would equal 5. Or if you've got it in log form and you have to rewrite it as an exponential form, then you would have 2 to the power of 5, again starting with the base, it's log base 2, so start with the base, draw a line at the bottom to the other side, so 2 to the power of 5, and that would equal 32. Few special cases with that. If you have log base a of a to the power of x, well, log base a and exponential base a cancel just like they did a minute ago, so you're just left with x. Also the other way around, if you have exponential base a and log base a, what do? Cancel! So you're left with x. If you have log base a of a, well, if you rewrite that in exponential form, it means a to the power of what equals what a, and it's just going to be 1. Also, if you have log base a of 1, what's that equal to? Well, if you rewrite it as an exponential, a to the power of what is 1? Well, it's going to be 0, so that equals 0. So switching between exponential form and log form. Here there was exponential form. Again, this is something you should be able to do. Look back to the lesson if you are unsure, and I'll go over every example. But for here, let's pick one. Start with the base. If you're writing it in log form, so the base is 4, so it's going to be log base 4 of, draw a line across to the other side, we get 64, so it's log base 4 of 64. That equals, draw a line back across, and we're left with 3, so a log base 4 of 64 equals 3. Going back the way, if it's in log form, rewrite it in exponential form. So again, we're going to stick with this one. So it's log base 5, start with the base, base bottom top. Start with the base, draw a line across the bottom to the other side. I've got 3, so it's 5 to the power of 3, and that would equal 125. We can use that to find out different values of x if there are certain unknowns. Here we've got log base for x equals 3. So we can rewrite that in exponential form to work it out. That's a lot easier than having to think about it in log form. So base bottom top, base is 4, so it's 4 to the power of 3, and that would equal x. From there, 4 to the power of 3 is dead easy to work out, so we can get this missing value. Look back to the lesson on that. It does go into some harder examples. Here we had to evaluate each of the following. So we had log base 2 of 64. Well, to evaluate that, I always set it equal to something. So let's set it equal to x. So x equals log base 2 of 64. Rewrite that in exponential form. It's in log form, it's difficult to work out. It just blows your mind. So you have 2 to the power of x equals 64. From there, you can easily work out what x would be. Might take a bit of time if you get bigger numbers, but it's simple enough to do. We then moved on to the second lesson with logs, which was looking at log rules. If you have log base a and log base a, and you're adding, so we've got the same base, well, you can multiply the x and the y together. If you're subtracting and it's the same base, log base a, we can divide the x by the y. Another rule, if you have a log base a of x to the power of something, that power you can bring down to the front. And you would then have n log base a of x. 2 that we already came across, log base a of 1 equals 0, and log base a of a equals 1. Applying these rules, we can then simplify, such as log base 10 of 5 plus log base 10 of 2. Same base, log base 10 and log base 10. What do you do with the 5 and the 2? Multiply! You got it. So that'd be log base 10 of 5 times 2, which is 10, so it's log base 10 to 10. And again, using this rule, log base a of a is 1, so that would just equal 1. If you are subtracting, it's log base 3 minus log base 3, so we can divide the 9 by the third. 9 divided by a third is 27. If you end up with something like this, log base 3 of 27, go off to the side, set it equal to x, and then write it in exponential form to work out what that is equal to. So in exponential form, base bottom top, 3 to the power of x equals 27, and then you can easily work out x. X works out to be 3, therefore log base 3 of 27 is 3. Yeah! Would you look at that? Log 4 plus 2 log 3, sometimes you will not be told what the base is. If you're not told the base, really, you can assume it's log base 10. You don't have to write it though, it's not important, you can miss it out as well. But here you're adding, so again you can multiply, but don't multiply the 4 and the 3. What would you have to do first of all? Yeah, you have to move the 2 up. So if you move the 2 up, that becomes an index. So you've got log 4 plus log 3 squared. You're just using this rule that is at the top of the page. From there, you know 3 squared is 9. It's log 4 plus log 9, same base, so you can multiply the 4 and the 9. So you get log 36. This example here, don't be put off if you have 3 terms. Again, you're wanting to think, ooh, I've got a number in front of log here. Mamma mia. So you want to move the 2 up, so it's log 3 squared. From there, work that out. Again, log, and log. base is all going to be the same, assume it's 10, don't bother writing it, and multiply, so 2 times the 9, and then divide that by 18. Gives you a log of something, log base something of 1, which means then you can apply this rule here. Log to any base, and then 1 is always going to give you 0. For some of these questions, what you'll notice is that there are other ways to solve them. That's not always the one method. With this one here, you can think, right, well, I'm applying the index rules to make that x to the power of -1, and then using this rule here to bring that index down. Or what you could say is, well, this rule here, just work backwards, is log something divided by something, so you can split that up into log x minus log y. So you could also say it's log 1 minus log x, and again log 1 is just going to be 0 using this rule here. So you get the same answer. So a lot of the time there will be more than one method of solving the problem. Here again, a couple of methods. With this one you can either think, right, well, for that I can bring this index down, so it's 3 log x minus 2 log x, 3 of them minus 2 of them is just going to give me 1 of them. Or you could also move this 2 up. So log x cubed minus log x squared, well then apply this rule here. When you're wanting to subtract, you're just wanting to divide. So it's x cubed over x squared, which is x. It's the same answer. You do get harder problems with this. There are plenty of examples if you look at them in that lesson. With this one here, you had to find out this value and show that y squared was equal to 81 bracket x plus 5. So again, you're just wanting to use all of these rules, and then you're rewriting in exponential form to get rid of the logs. After that, we then moved on to solving log equations. Yeah! And we did that using log rules. Yeah! That we learned about in the previous lesson. Here, to solve this equation, we've got an x. That is what we want to work out. Because it's log base a, log base a, log base a, it's a log base a, what we can do is we can multiply the 5 and the x together to get 5x. From there, if you have log base a and log base a, well, you could really cancel them out, but the way you do that is you take the exponential of base a on both sides. So you've got a to the power of log base a of 5x and a to the power of log base a of 40. From there you've got exponential base a, log base a, they cancel, leaving you with 5x, and the same on this side. Exponential base a, log base a, they will cancel. And from there you can find the value of x. With this one here, again, you want to find the value of x. Just apply those log rules. You've got the half, you can move that up, so it's x to the power of a half. It's log base 2 minus log base 2, so you're going to be dividing these. After you get log base something, if something equals something, well, rewrite it in exponential form. It just makes it far easier to work out. So, in exponential form, base bottom top, 2 to the power of 1 would equal this in the brackets. And from there, you can work out the value of x. For any of these, if you are unsure, please look back at the individual lessons. I'm going over this very quickly. What's the point in the logs? Why would you use them? Well, if you have something like 5 to the power of x equals 4, it's very difficult to work out what this index would be. If it gave you this before you learned about logs, really you'd be there forever just putting in different numbers and trying it and then getting down to a decimal and trying to narrow it down. What you can do though is you can use logs, because one of the rules, this rule here, allows you to bring the index down. So if you have logs on both sides, you can bring this index down and then you can deal with it that way to find out the value. So here there is a calculator button which says log, and really that is log base 10. If you take logs of both sides, you have to do the same thing to both sides for it to remain equal. Well, take log of both sides, so log base 10, and then from there you can bring this index down. So you'd have x log base 10 of 5 equals log base 10 of 4. And then from there, to get x, we can divide both sides by the log base 10 of 5. This example here, very, very similar. You're looking at it and what should jump out is that x is an index. Woo! So to get that, to bring it down, come here. What you've got to do is you've got to take logs of both sides. So take logs of both sides, bring the index down, and then from there get x on its own by dividing both sides by log base 10 of 2. Something else that we can do with logs, well, if you think about it, if you have e to the power of x, you can take its inverse as well. The inverse of e to the power of x is known as a natural logarithm. Woo. And the way you write it is either a log base e of x or, more commonly, ln x. Just like using the log button, the way we did a few seconds ago, take the logs of both sides, well, we can also take ln, it's still logs of both sides. But if e is involved, you tend to use ln to make the rest of the problem easier, because ln means log base e of e, which is going to be equal to 1 if you have ln e. For example, if you want to solve this one, e to the power of x equals 9, well again take the logs of both sides. E is involved, so use natural logs. So you have to have ln of both sides. From there, use the rule to bring the index down. So you'd have x ln e equals ln 9, and ln e is log base e of e, which is 1. So that just cancels out, leaving you with x equals ln 9. And from there, just put that into your calculator. The questions do get a little more worded as you go on through that, but again, you're given a formula with e that is involved. Part A of this one was easy enough to work out, but for part B, we ended up getting down to e to the power of negative 2t equals a half. Again, we're wanting to work out this index. E is involved. To bring the index down, we used natural logs. So ln both sides. From there, bring the index down, ln e goes to 1, so we're just left with negative 2t equals something. And from there, it's easy enough to work out t. Again, we've got this question here. It's a fire, and it's described by a law, a equals a naught e to the power of kt. Again, it's this formula that involves e. Look back to this example if you're wanting me to go over it, but you get down to the same idea. You get e to the power of 1.5k equals 2. Whenever you get down to that, apply the logs of both sides. Because e is involved, use natural logs, so ln both sides, and then you can bring the index down. ln e goes to 1, so you're left with 1.5k equals, and then you can divide both sides by 1.5 to find k. The questions do go on, they maybe get a little more worded, such as this one here, but it's the same idea. With this one, I wanted to point this out because this is something that comes up a lot. It's talking about the half-life of a substance. Part A is easy enough to work out, but for part B, well, it says here the half-life of a substance is the time taken for the amount to decrease to half its original amount. What is the half-life of this substance? Something that you have to be able to realise is that after a certain amount of time, well, you're going to have half the original amount. So a naught here in this question was the original amount, so after a certain amount of time, you will have half a naught. So what you can do is you can replace at with a half a naught. From there, divide both sides by a naught, so you're left with a half equals a to the power of, and again you've got something up here that you're wanting to find. It's the negative 0.002t. We want to find t. How do you do it? What do you do? Good, natural logs, because e is involved. Take natural logs of both sides, so ln a half equals ln all that. Bring the index down, ln e then goes to 1, leaving you with negative 0.002t, and from there it's dead easy to find out what t will be. Experimental data was what we looked at after that, and if you have a graph of x versus y, such as this here, then there's a good chance it's going to be of the form y equals kx to the power of n. A lot of the time in physics and other sciences you will collect data and you will represent it in a graph, something that looks like this. Something that makes graphs easy to compare though is when you have a linear relationship, if you have a straight line. So we can think, right, well, if we take logs of both sides, we can end up getting down to something that's in the form of y equals mx plus c, if instead of y and x, we've got log x and log y. So a lot of the time, if you're doing any sciences, you will have a straight line graph, but you won't have x and y, you'll have log x and log y. And what you can do with that then is, what we were doing, is you can rewrite that in the form of y equals kx to the power of n. The way you do that, if we're given, for example, this graph here with log base 10 of x and log base 10 of y and 2 points, well, you're thinking it's a straight line, y equals mx plus c. But we're not given y, we're not given m, we're not given x, we're not given c, so write in what they're all equal to. Instead of y, we've got log base 10 of y. Instead of x, we've got log base 10 of x. M is just the gradient, do that the same way. y2 take y1 over x2 take x1, ba-dum, 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 ba-dum. C is going to be 3, and from there you can sub them into y equals mx plus c. From there, if you look at any marking schemes, there's about 4 or 5 different methods for working that out. The way I like to do it is to take the logs to one side and then rewrite it in exponential form. So for this, if you have something in front of log, move that up here so it becomes an index. So you'd have log base 10 of x to the power of 1/2. From there, move the log base 10 of x to the half to the other side, or subtract it from both sides. So you have log base 10 of something minus log base 10 of something. And if you've got log base 10 of something minus log base 10 of something, you can divide. So it goes to log base 10 of this divided by this. From there, if you've got log base something of something equals something, rewrite it in exponential form. Base bottom top, so it's log base 10, so you'd have 10 to the power of 3, and that would equal this y over x to the power of 1/2. From there, well, in this one we're asked to work out the values of k and n. Don't leave it as 10 to the power of 3. You know what that would be. The other examples were very, very similar. There's quite a few of them that I did for you, but this one here, the line was sloping down. The only difference that makes is you will get a negative gradient. You can treat the negative gradient two different ways. What I did, just so it was different from the other examples, was I left the negative there and I moved the index up, just the 2/3. So I had negative log base 10 of x to the power of 2/3. From there though, you still want to get logs on the same side. So add that to both sides. So you have log base 10 of y plus log base 10 of x to the power of 2/3. And from there, log base 10 is log base 10. You're adding, so you're multiplying. That was different from the other examples. The other ones was dividing. You get the same answer though in the end. Here, write it in exponential form, so 10 to the power of 0.4 equals this yx to the power of 2/3, and from there it's easy enough to find out what y is equal to. Just watch out for these if you are asked for so many decimal places. Just use your calculator. After that, with this one here, we want a root. We want p root of qx to the power of r. How's this one different? Well, you're not given c. So the only difference with this one, even though it looks a bit more complicated, is the exact same method. But you have to use y equals mx plus c, some National 4, National 5 knowledge in order to work out c. And from there, you can sub in the different values. Take the logs to the same side, use your log rules, rewrite in exponential form, and then get y in its own. Again, a little bit of knowledge in indices is required, but not too tricky. Instead of log x versus log y, you could also have x versus log y. And if you do have that, it can be shown that you can write that equation in the form y equals a times b to the power of x, as an exponential, in other words. So, with this one here, we've got x versus log base 3 of y. We've got a gradient of 3 and it's passing through the point 0, 0. For these questions, you want to do them the exact same way. I always go off to the side, think it's a straight line, it's y equals mx plus c, and write down what y, mx, and c are equal to. From there, sub them into y equals mx plus c, and from there you can easily rearrange that to get down to whatever y is. If you're unsure, look back to that lesson. With this one here, again, it's the same idea. We've got x against log base 4 of y. We've got this point 0.2. We've got this point 0.86. So again, straight line, y equals mx plus c. Write in what y, mx, and c are equal to, and then sub them in. This one is slightly trickier though, because we've got log base 4 of y equals all of this side. It is difficult to get y in its own, so what you need to do is you need to rewrite it in exponential form. So, base bottom top, it'll be 4 to the power of all of this equals y. From there, use your knowledge of indices. You know, if you've got 4 to the power of half x plus 2, you could split that up. So it'll be 4 to the power of half x times 4 to the power of 2. Because you know if you've got the same base, you would add these indices. So you're undoing that. From there, if you've got 4 to the power of a half times x, well again, you know you could undo the rule where you've got 4 to the power of a half to the power of x, where you're timesing them together. So undo that. Power of a half is the square root. So you'd have the square root of 4, which is 2, so it's 2 to the power of x, and 4 squared is obviously 16. So you can write it as something times something to the power of x. So 16 times 2 to the power of x. Look back to the lesson if you're wanting a bit more detail. We finished off just going back to log graphs. Olivia, it's your favourite, isn't it? Yeah! So, log graphs, we touched on them in the third unit. We have log base a of x, and it's the inverse of an exponential. Our exponential always passes through 0, 1 and 1a. Our log graph will pass through, flip the x and the y, 1, 0 and a 1. The y-axis is an asymptote for a log graph, which means that the graph will get closer and closer and closer and closer to it as it goes down towards negative infinity, but they will never, ever, ever come into contact. It will just get closer and closer and closer. For this part, you need to be aware of your graph transformations and you need to apply them. You need to think about what's happening. With this one here, well, a log graph always passes through 1, 0. Instead, it's passing through negative 2, 0. It's moved 3 places to the right, which means in the brackets here, you would have plus 3. A positive 3 would move it 3 places in the negative direction. So it's really applying your graph transformations to the log graphs. With this one here, it's the same idea. It's thinking, right, it should be passing through 1, 0. It's passing through 3, so it's moved 2 places to the right in the positive direction, which means in the brackets you'd have an x take away 2. So b is going to be 2. From there, use any other knowledge that you have. Here we're also told 4, 3 in order to work out the value of a. You're subbing in, and then that's dead easy. Other examples, if we have a log base 5 of x and we have to draw a log base 5 of x plus 1, hopefully you remember, a log graph passes through 1, 0 and a 1. In this case, because it's log base 5, it'll be 5, 1. And the plus 1 in the end, well, it just shifts every single point up 1, so your graph's just going to be moving vertically up 1 unit. For part B, we had to draw the graph of log base 5 of 1 over x, so for that you need to think about rewriting it. You need to think about getting it into a form where you know what's happening to it. Here, you could either rewrite that as x to the power of negative 1 and move the negative 1 down, so it's negative log base 5 of x, or you could split it up, so it's log base 5 1 minus log base 5x. A log base 5 1 is going to be 0 using your log rule, so it gives you negative log base 5 of x. Either way, you're changing log base 5 of x from a positive to a negative, and if you, instead of having f of x, you have negative f of x, what you're doing is you're reflecting the graph in the x-axis. So this x-axis becomes your mirror, and you're just reflecting your points over, just like that. And with this example here, sometimes what you need to do is just sub in different points in order to work out different values. Here we're told this point q2, you know x is q, y is 2, sub them in, and you can work out what q will be. That's a very brief summary of logs and exponentials. It is the final one. So well done for reaching the end of the course. And best of luck with any test, any exam. Woo! We have made it. Try some of these questions, see how you get on. Any problems? Give me a shout. There.